Right.
Hi, my name is Carl Sabottke, and today I'm excited to talk about my work with several great collaborators on novel approaches for learning radiology AI for medical students, residents, and radiologists new to computer programming. For this talk, we're going to highlight some challenges related to radiology AI education and discuss methods for overcoming these issues. We have no disclosures. So let's talk about some of the potential obstacles. At a high level, these are lack of appropriate hardware resources, lack of relevant background knowledge, and then lack of available time. For the hardware issue, if we are trying to train AI models on local hardware, then acquiring an appropriate GPU can be quite costly, and getting a local AI workstation might cost thousands of dollars depending on the type of hardware being acquired. This can be a major barrier to entry in order to pursue a potentially casual interest in learning more about radiology AI. However, a great solution is using cloud-based GPU resources like Kaggle and Google Colab. These are not ideal solutions for projects using local clinical data, which might have specific HIPAA-related restrictions and would be a poor fit for using cloud-based GPU resources. However, these cloud-based resources are a great way to start out working with public data sets in order to learn more about radiology AI. Kaggle even hosts several competitions, including an annual RSNA challenge, which can be a great way to jump into relevant radiology AI projects and get a feel for state-of-the-art techniques. Now, while some radiologists, residents, and medical students might potentially have very deep backgrounds in mathematics or computer programming, this is not universal and can definitely be a major impediment to further exploring AI. However, there are a ton of great resources meant to provide introductions to computer programming or introductions to AI, which do not expect a strong background in either computer programming or mathematics. For example, Jeremy Howard's Fast AI tutorials listed here are a personal favorite of mine. This is also where we have elected to focus our efforts. We've been working on designing a series of tutorials related to hepatic image segmentation using AI. And these tutorials are meant to be relatively quick and easy to follow without expecting much background knowledge of the several mathematical and computer programming concepts employed within the tutorials themselves. Hosted on GitHub, we have created a series of 4 tutorial lessons related to AI-driven hepatic segmentation. And we have split these lessons between 6 different notebooks in order to keep the total needed runtime for each Jupyter notebook relatively low. Predominantly, we have focused on UNet segmentation of the liver on CT and MRI images, but we also cover the basics of working with imaging data and basic concepts in radiomics. The overall set of tutorials is designed to be completed in about 4 to 6 hours, so this would take about 1 day of focused attention, or could be split over approximately 1 week using 1-hour blocks. Also, so that GPU resources are not a barrier to entry, this set of tutorials is designed to be readily runnable with Google Colab based on the Jupyter notebooks hosted on GitHub. This is a summary of the designed tutorials, which start with the basics of working with DICOMs using Python, and then jump straight into using FastAI and the public chaos dataset of CT and MR images in order to perform hepatic segmentation using UNets relatively rapidly. Then we review some basics of radiomics, and then in the final pair of notebooks, we go back to the UNet segmentation performed in lesson 2 and review some of the finer modeling details as well as potential modeling pitfalls. So based on even the relatively simplified code provided in the tutorial, here's an example axial CT slice, which shows the manually drawn target segmentation provided by the chaos dataset on screen left and the predicted segmentation on the right side of the screen. We also stress within the tutorial series the importance of reviewing cases manually, which have high loss function values. So essentially, these high loss function value cases are the worst predictions the model is making. These types of cases can be really important for understanding potentially clinically concerning errors that the model is making, or for understanding if there might be fundamental issues with the labeled training data or the ways that the model is processing the data. Here's another example prediction for an axial MRI slice, which shows that the segmentation is a reasonable rough approximation, but definitely not perfect if we look at it with much scrutiny at a pixel-specific level. So our key takeaways are that hands-on experiences with AI programming can be vital to improving radiologists' understanding of AI and AI tools that might be incorporated into clinical workflows. Starting with cloud-based GPU resources and browser-based code execution is a great way to get started working on AI projects without having to commit to purchasing any new computer resources. Additionally, the growing plethora of online tutorials makes it so that concerns about lacking sufficient background knowledge no longer need to be a major excuse not to start engaging with the development of AI models. Thank you.